So it's my pleasure to introduce today's speaker, Tamar Janelidze-Gray from Cape Town, University of Cape Town. She will tell us about S-protomodular categories, a new approach. So please, Tamar.
Thank you very much, and thank you for organizing these seminars and especially for inviting me to give a talk here. I'm going to start sharing my screen, and if I may, I'm going to turn off the camera while I'm giving a talk, and then I'm going to turn it on again. No, sorry, this is the wrong screen. Where are we? May I just confirm that you can see my screen?
Yes, we can see. Perfect.
Yes.
Sorry. No. Okay, let me just try again. Sorry about this.
No, take your time. I mean, no rush.
Okay, let me try again. All right. So I'm going to begin. Before I go into the details of my talk, I'm going to start with a bit of background, and especially I'd like to give a bit of a motivation to where this research is coming from and what it is related to. And I'm going to start with something that is very well known in the category of groups. In particular, we know that in the category of groups, split epimorphisms, they are essentially the same as group actions. Now, if we move on to the category of monoids, we cannot say the same thing, because although monoid actions do give rise to split epimorphisms, the converse is not always true. However, as it was proved by Montoli, Martin Ferreira, and Sobral, if we take the category of monoids, there is a special class of split epimorphisms, namely Schreier split epimorphisms, which turn out to be essentially the same as monoid actions. I am going to define Schreier split epimorphisms later on in my talk more explicitly, but for now we can think of them as surjective homomorphisms between monoids, which have a chosen splitting, which is also a homomorphism, and moreover, there's a special condition on this surjective homomorphism. Moreover, they've proved, and together with Dominic Bourne, that in the category of monoids, Schreier split epimorphisms satisfy some of the important properties that are closely related to be satisfied, or that are classically known, so to be satisfied by all split epimorphisms or groups. But they're not necessarily satisfied by all split epimorphisms of monoids. And among them is the very well-known split short-5 lemma. And I'm just going to spend a few minutes on split short-5 lemma because I'm going to need it in order to define protomodular and then later on S-protomodular categories. So we are now in a pointed category, and by pointed category, we mean we have initial and terminal object and they're the same. And given a commutative diagram where the top and the bottom rows are exact, and by exact we mean that K is the kernel of F and K prime is the kernel of F prime. Now here we mean categorical kernels, and of course in groups and algebras in general, they're the usual kernels, but here in categories we define it using universal property. And the short-5 lemma, well, split short-5 lemma states that if F and F prime are split epimorphisms and U and V are isomorphisms, then the middle morphism W is also an isomorphism. Now, this condition actually goes back to 1950s when MacLean, he wrote a paper, Duality for Groups, and he tried to give a list of axioms that would capture the properties of groups and algebras in general. And in fact, in that paper, he mentions extension isomorphism theorem, which actually is essentially the same as the non-split version of this short-5 lemma. Now, it turns out that if we take a category which is pointed and which also has finite limits, requiring that in that category split short-5 lemma holds is the same as to say that the category is protomodular in the sense of Bourne. Protomodular categories, they were introduced by Dominic Bourne, and he proved that, well, in the initial definition, it wasn't required for the category to be pointed or for it to have limits, finite limits. But then later on, it was proved that in case when a category is pointed and has finite limits, then category is protomodular if and only if the split short-5 lemma holds in that category. So now, informally speaking, we can say that, well, first of all, groups, well, abelian groups and in general groups and even more general algebras, they satisfy this split short 5 lemma. But if we take category of monoids and we consider split epimorphisms in the category of monoids, they do not satisfy this lemma. And in fact, as I mentioned earlier, it turns out, and this was put by Bourne, Montoli, Martin Ferreira, and Sobral, that if we replace in that split short 5 lemma f and f prime, if we take them to be these special Schreier, well, split Schreier epimorphisms in the category of monoids, then it does turn out to hold. And accordingly, Bourne, Martin Ferreira, Montoli, and Sobral, they introduced the notion of an S-protomodular category. And it is a pointed category, which is finitely complete. And in that category, we have a distinguished class of split epimorphisms, which they also call them points. And so it is defined as S-protomodular category, it is defined as a pair, and there are conditions imposed on both the category itself, C, and on the special class of split epimorphisms. And they proved that if we take C to be category of monoids, and if we take S to be the class of all Schreier split epimorphisms, then that will form an S-protomodular category. Moreover, and I'm quoting this from their paper, they proved that S-protomodular categories satisfy many partial aspects of the properties of Maltsev and properties and protomodular categories, which includes the split short 5 lemma for S split exact sequences. In other words, quickly, let me go back to the diagram. So here, f and f prime, instead of saying they're split epis, we take them to be split Schreier epimorphisms. Or the fact that the reflexive relation, reflexive S relation is transitive, and this is the Maltsev condition. Now, I'm not going into details of Maltsev categories because I'm not really going to need it in this talk, but let me just briefly mention a category is Maltsev where if every reflexive relation is transitive, which implies that every reflexive relation is an equivalence relation. So here, in the S-protomodular context, we take only those relations where well, if it's reflexive, it's got a splitting, where the split epis are in S, in the class S. But now we ask the following question. So as I said earlier, we take Schreier split epimorphism in the category of monoids, and these are those surjective homomorphisms which has chosen splitting with certain conditions, but that splitting is a homomorphism. And now we want to see whether it is possible to develop a similar structure, but we don't necessarily take those surjective homomorphisms where the splitting is a homomorphism. So we take those surjective homomorphisms with a special condition on it, such that there exists a splitting which is not a homomorphism, and yet we want to still be able to develop similar theory. And so what we're going to do now is I'm going to try and answer the following question. What happens if we replace the Schreier split epimorphisms with so-called regular Schreier epimorphisms in the category of monoids? And again, I will define this later on explicitly, but for now, we can think of regular Schreier epimorphisms in the category of monoids as surjective homomorphisms with a special property where the splitting is not necessarily a homomorphism. All right, so in order to answer this question, I'm going to need to introduce various definitions and notions and also mention a few theorems. I'm not going to prove the theorems, but I will still point them out. So now we are moving to the pointed category with finite limits. By the way, I didn't mention what we mean by finite limits. Well, of course, it's got its own definition, but in our context, what we need is we want it to be pointed and then we want it to have pullback. So if a category has, well, terminal objects, and we do have it because it's pointed, and if it's got pullbacks, then it's the same as, it's equivalent to saying that the category has all finite limits. All right, so the first notion that we would like to introduce is what we call a generalized point. And a generalized point in C is a pair, Fg, so it's a composable pair of morphisms such that the composite is a pullback stable regular epimorphism in C. So in other words, what we're doing is because we want to now move from split epimorphisms, which have the splitting as a homomorphism, we now take composable pair of morphisms where the composite is not just an identity, but it's not necessarily identity, it's just a pullback stable regular epimorphism. And let me just make sure that well, everyone remembers what is a pullback stable regular epimorphism. So first of all, what is a pullback? And I'm going to use the same notation. So we take Fg, And if we have any other morphism X by a pullback, we mean, well, we can think of it as a diagram or as a triple. So we have an object over here with two morphisms pi1 and pi2, and it's such that the diagram is commutative and it has a universal property. So we have H1 and H2 such that FGH1 is equal to XH2, and we have a unique morphism H making these two new triangles commutative. And now by pullback stable regular epimorphism, what we mean is that we have FG, which is a regular epimorphism. And by regular epimorphism, well, we have a categorical definition. It's defined as a co-equalizer of pair of morphisms, but we can think of them, for example, in the case of groups and algebras in general, they're just surjective homomorphisms. So by pullback stability, we mean that if FG is a regular epimorphism, then at the top, this morphism over here, pi2, is also a regular epimorphism. And in terms of notation, well, we will sometimes write the generalized point as a pair FG, or we will just use the following sequence. We'll write it as a diagram. Now we have a little remark. It's a well-known fact about regular epimorphisms, which says that if we have a composite FG and if it's a pullback stable regular epimorphism, then it automatically follows that F is a pullback stable regular epimorphism. And now I'm not going to give proof, so it might not really be visible why we need this, but we do need F to be a regular epimorphism as well, and it's quite often used in the proofs of the theorems that I'm going to mention. We have another definition. So what we want to do now is we want to construct a category of generalized points, and of course, in order to do that, we need to define what a morphism is between such generalized points. And it's defined quite naturally. We define it component-wise. So it's a triple alpha, beta, gamma, as indicated in this diagram, such that both of these squares in the diagram are commutative. And in terms of notation, we're going to denote the category of generalized points by G, PTC. And the reason where this notation is coming from is actually from the category of points in the sense of Born. And let me quickly recall that as well. So category of points in the sense of Born, it's the objects are split epimorphisms, so he calls split epimorphisms points. I see I've got a little mistake here. It's composite FG should be 1B. Sorry about that, not 1A. And then the morphism between split epimorphisms are just diagrams of this form where we have commutativity in both directions. So F prime U equals to VF, and then G prime V equals to UG. And so now, if going back to our definition, so if we take now those generalized points where the composite FG is identity, then this gives us exactly the category of points in C. And so in the case when the composite is an identity, so in the case when the generalized points F is a split epi, then we will call such generalized points split generalized points. So they are the same as points in the sense of Born, so just split epimorphisms. We need another definition, which is a notion of a strong generalized point, and this is coming from generalizing the notion of a strong point in the sense of Born. So we say that a generalized point, Fg, is a strong generalized point if G and the kernel of F are jointly strongly epic. Now, what do we mean by that? So in this diagram, I didn't write down F not to make the diagram too messy. So we have the generalized point Fg, and K from K to A is the kernel of F. So remember, F was going from A to B. And those two morphisms, K and G, are jointly strongly epic if we take any monomorphism M going from M to A, such that it factors through both K and G. So we have some morphisms U and V such that MU equals to K and MV equals to G, then it should imply that M is an isomorphism. This notion, as I said, it relates to the notion of strong point in the sense of Born, and I've just put in some references. So split generalized point, which is strong, it is the same as strong split epimorphisms in the sense of Born, and it's also known as a regular point and also a strong point. So now the next thing that we're going to need is we're going to need to define a pullback of a generalized point along some morphism. So given a generalized point Fg, and we have some morphism x, well, this x from x to b, we define a pullback as follows. So we first take the pullback of f along x, then we take g from c to a, and then we take the pullback of fg along x. So we get this big commutative diagram. Pi1 prime is the first projection of the pullback, and then we get a second projection from this object going all the way to x. But then because this right-hand square is a pullback, we get an induced morphism using the universal property or using the definition of a pullback going into over here, which makes this right-hand square commutative. And I denote it by g cross 1 because it is actually the morphism that we get there. And a very simple property about pullback states that if in this diagram, but also in general, when we have a diagram like this, if the right-hand square is a pullback and then the outer rectangle is a pullback, then the left-hand square is also a pullback. Yes, so one thing that I need to mention here, by definition, of a generalized point, we say that the composite Fg is a pullback stable irregular epimorphism, and therefore now we've got this pullback. So at the top, the pair that we get g cross 1 and pi2, that is going to be also a regular epimorphism, and we call that pair to be the pullback of Fg along x. So that's a pullback in generalized points in C. All right, now continuing further, we have the following theorem. I'm not going to prove the theorem, but it's a theorem that we use a lot in the following theorems. And the theorem states that given a commutative diagram, and this is the pullback diagram, which I've just defined above, if it turns out that kernel of pi2 and g cross 1, so at the top, they are jointly strongly epic, then kernel of f and g are also jointly strongly epic. In other words, the theorem says that if we have a generalized point fg and we take a pullback of that along some morphism x, if at the top we get a strong generalized point, we already know that it's a generalized point, and so if more of it is strong, then also at the bottom we have a strong generalized point. Now, if we take this pullback diagram, and in this pullback diagram we replace x with the composite fg itself, so in other words, we're taking now the kernel pair of fg, we obtain the following diagram. And in this diagram, so what we have now, because we replaced x with fg, we end up with pi2 being a split epimorphism. Now, why is pi2 a split epimorphism? Because we take c and then we go into a using g, and then from c to c, we of course have the identity morphism. It makes, then we get the outer diagram commutative, and by definition of a pullback, we get an induced unique morphism going here, which makes, in particular, this triangle commutative. So the morphism I denoted by G1C, this is the morphism that is induced by G and the identity morphism. And because the triangle is commutative, we end up with pi2 being a split epimorphism, with a splitting being this morphism over here. And similarly, we obtain that the composite pi2 g cross 1 is also a split epimorphism for the same reason. We take C and then we go into C with the identity, but then we can go all the way from C down into here with an identity. And because the right hand, not the right hand, the outer rectangle is a pullback, that gives us the induced morphism from C to here, which should make this big triangle commutative, which means exactly that pi2 g cross 1 composed with this gives us the identity. So if we replace x with a composite fg, it gives us that at the top pi2 is a split epimorphism, and also the composite pi2 g cross 1 is a split epimorphism. And now using this diagram, going back here. So now if we just look at the top part of this diagram and generalize this, so we don't use specifically pi2 and g cross 1, and we just look at a diagram of this form where we have a generalized point fg at the bottom. We've got f is a split epi with a splitting 1b, and g is a split epi, fg is a split epi with a splitting h. Then the proposition says that if kernel of f and s are jointly strongly epic, then fg is a strong generalized point. So in other words, if kernel of f and s are jointly strongly epic, then kernel of f and g will also be jointly strongly epic. So now if we apply this proposition to this diagram over here, then what does it give us? Then that proposition in this specific diagram will tell us that if the kernel of pi2 and this morphism over here are jointly strongly epic, then kernel of pi 2 and G cross 1 should also be jointly strongly epic. And then let me quickly go back over here. Then this theorem tells us that if at the top we get a strong generalized point, then at the bottom we also have a strong generalized point, so Fg. So now putting this theorem together with this proposition, we obtain the final corollary, which states that if G and the induced morphism to the pullback G1C and kernel of pi 2 are jointly strongly epic, then Fg is going to be a generalized strong point. All right, so these are some of the preliminary notions that I wanted to introduce, and now I think we are ready to define what we call, or what Dominique Boone calls, S-protomodular category, and then we're also going to define what we call T-protomodular category, and then we will see how these two things relate to each other. So now I'm going to consider two classes. S is going to be the class of points, so in the sense of Bourne, so class of split epimorphisms, and then by T I'm going to denote a class of generalized points. So we are again in a category which is pointed and where we have all finite limits. And let's start looking at conditions that we have on the class S. So first of all, we want S to be pullback stable. So if a morphism is in S, then when we take the pullback at the top, the morphism we obtain is again in S. We want it to be closed under finite limits in points in C. And then the third condition that we have is that all elements are strong. So every point is strong, or every split epi is strong. So when a category which is pointed and finitely complete satisfies these three conditions, then this category is called an S-protomodular category, and this notion is due to Bourne, Martin Ferreira, Montoli, and Sobral. And now let's see what conditions we put on T, where now we take T to be class of split class of generalized points. And in fact, I've put these two sets of conditions together so we can see where the conditions that we have in condition 9 are coming from and how they are related to the conditions in condition 8. So we have again pullback stability. T is pullback stable. It is closed under finite limits, but now we say that it's closed under finite limits in generalized points in C. We again have that all of its limits are strong. So far ABC in condition 9 is exactly the same, well, essentially the same as in condition 8. And then we have one extra condition, and this is not it's quite a natural condition to have here. So condition 9D says that if we have a diagram as we have over here on the right hand side, where Fg is a generalized point and the right hand square is a pullback, then the top row belongs to T if and only if the bottom row belongs to T. So first of all, if Fg is a generalized point, because it is pullback stable, we already know that at the top the composite is also going to be a generalized point. And by the previous theorem we mentioned before, if at the top we know that we have a strong generalized point, and at the bottom is also a generalized point. So in other words, what we say in this condition is that if the top part ends up being in T, then we already automatically know that at the bottom we have a strong generalized point. So this condition just tells us that that generalized point should also be in our class. And then similarly to go up, so if Fg is a strong generalized point, then by condition of A, or by pullback stability at the top, we get again a strong generalized point, and then we just require that to be in T whenever the bottom one is in T. And so now we define, or we introduce the notion of a T-protomodular category as follows. If we have again C, which is pointed and finite limits, and in that class T, and so in that category T is a class of generalized points. If T satisfies conditions 9, A, B, C, and D, then we say that C is a T-protomodular category. And now the question is whether these two, the definitions that we have, whether they are the same or whether different, or if they, in what way are they related to each other. Yes, I've already said that. So now it turns out that they are actually not, they're not two different notions, but T-protomodular category is just a different approach to S-protomodular categories. In other words, it's, well, more specifically, it's a non-split approach to S-protomodular categories. And this is shown by with this theorem. So if we take the collections of all classes of points in C, and then if we take the collections of all generalized points in C and we denoted them by bolts S and bolt T, then it turns out that we have a bijection between the two. So we've got maps F from T to S, and then we have G from S to T. And this bijection is described as follows. So how do we define F? So we start in T, we take a class of generalized points, we call it T, right over here. And then we take all those split epimorphisms in points, or we take all those points where that when we take that composite GF, which is an identity because we are because it's in points, that split epimorphism is a split generalized point. So that split epimorphism ends up being a generalized point. And then how do we go back? Well, now we start in S, so we take a point, and then in order to go into the collection of generalized points, what we do is we take all those generalized points such that this pair is a split epimorphism or a point in C and in S, sorry. So, and just to recall what that is, so we had this diagram before. So we have FG generalized point. When we take the pullback of FG along FG, so we get a pullback here, and then this was the induced morphism that we got into the pullback. So GS is the set of all those generalized points such that when we form those pullbacks, what we get at the top, the pair G1C and pi2 becomes a point in S. So these maps F and G, they turn out to be inverse to each other. Well, they're bijections, and I'm not going to go through the proof. It's quite a lengthy proof, so there are quite a few things to be proved here, right? So first of all, we need to prove that FT, this thing ends up being an S-protomodular category, and then we also need to prove that GS, when we form this set, this forms a T-protomodular category, and then in addition, we'll have to prove that the composites FG and GF are identities. All right, so now I'm going to, I think we are now ready to move on to the category of monoids, and we're going to see now how that theorem helps us to find the connection between split Schreier epimorphisms, regular Schreier epimorphisms, and what we also introduce generalized Schreier epimorphisms, and we're going to see how those three are all related to each other using the theorem that we've just mentioned. So we are now in the category of monoids, C is a category of monoids, and we're going to use additive notation. And what is going to be a generalized point in the category of monoids? Well, it's just going to be a composable pair of homomorphisms such that the composite FG is a surjective homomorphism of monoids. And I'm going to now give different definitions, which is by various authors. So I'm going to start now with a Schreier point, which is the same as split Schreier epimorphism. And it's defined as follows. And I'm going to now define them in terms of generalized points. Now here, we take a split generalized point, which we can think of them as just split epimorphism or a point. So a point GFG, we've got this over here, is said to be a Schreier point or a split Schreier epimorphism if the following conditions hold. So for every A in A, there should exist a unique element in the kernel of F such that A equals to K plus GFA, and plus is the addition that we have in the monoid. So for every element in A, there exists a unique element in the kernel of F such that A equals to K plus GF. So this is a notion, this gives us the definition of a split split Schreier epimorphism. All right, now the next definition, the next notion that we want to define are regular Schreier epimorphisms. And before I do that, I'm first going to define a Schreier epimorphism. So now suppose we have a surjective homomorphism between monoids. I'm first going to define a representative element of some element B in B. So an element A in A is said to be a representative of an element B in B. If, first of all, it's in the preimage, so FA equals to B, And then if we take any other or every other element A prime in A, such that it also goes into B, so such that FA prime equals to B, then there should exist a unique element in the kernel of F, we call it K, such that A prime equals to K plus A. So this is a representative element, or a representative, sorry, of an element B in B. And now having this, we can define a Schreier epimorphism as follows. A surjective homomorphism F between monoids A and B is said to be a Schreier epimorphism if for every element in B, if every element in B has a representative. And now we move on to regular Schreier epimorphisms, and we say that, well, F is said to be a regular Schreier epimorphism if it is a Schreier epimorphism, so if every element in B has a representative, and the set of all representatives of elements of B is a submonoid of A. So we have three notions. We have split Schreier epimorphisms, which says that every element in B, so F is from A to B, every element in B has a representative. We have, well, before that we had a Schreier epimorphism, and then, no, sorry, I made a mistake. We have Schreier epimorphism, which is that for every element in B, it has a representative. Then we have a regular Schreier epimorphism, which is a Schreier epimorphism such that the set of all representatives in B are submonoid, and then before that we defined split Schreier epimorphisms. All right, and now we're going to introduce what we call a Schreier generalized point. And given a generalized point, Fg, so again, Fg, it's a composable homomorphism such that the pullback is such that Fg is a pullback stable regular epimorphism. And it is said to be a Schreier generalized point if for every element A in A and for every element C in C, such that, or with Fa equals to Fgc, there exists a unique element in the kernel of F such that A is equal to K plus Gc. And now we want to see or describe the connection between Schreier points, so split Schreier epimorphisms, regular Schreier epimorphisms, and Schreier generalized points. So we have the first theorem. We have S, which is, so suppose, or let S and T be classes of Schreier points. So S is a class of split Schreier epimorphisms, and then T is a class of this, what we defined, Schreier generalized points. Then we have to have the following. So first of all, C is an S-protomodular category, and this was proved by Bourne, Martin, Ferreira, Montoli, and Sobral. And then it turns out that if we take the Schreier generalized points, then C is a T-protomodular category. And now finally, using the bijection that we had before, we can relate S-protomodular and, well, split Schreier epimorphisms and Schreier generalized points. So S and T correspond to each other under the bijection described in the theorem earlier. Sorry. All right, but now let's be a little bit more specific. And what results do we have? Well, given a monoid homomorphism F from A to B, it is a regular Schreier epimorphism if and only if there exists a monoid homomorphism G from C to A, which makes Fg a Schreier generalized point. So we have a connection between regular Schreier epimorphisms and this Schreier generalized points. And now what does this give us? Well, this now allows us to give a categorical definition of regular Schreier epimorphisms as follows. So this is, we need theorem 16, but also from this theorem over here that we have back. And so what do we have? So a monoid homomorphism F from A to B is a regular Schreier epimorphism if and only if there exists a monoid homomorphism G from C to A, such that Fg is surjective, and this pair pi to G1C, which is, again, just to recall quickly, this was obtained by taking the pullback of, we take the pullback of G along Fg, is a Schreier point. And I think that's it. I'm afraid I'm a bit my talk was a little bit shorter than I expected. Let me just give some references. And then we have one more page.
Oh, I see.
So shall I go back?
Are you done with the talk?
Yes.
I see. So let me stop the recording.